All right, so now that we have a definition for the density matrix for both pure states and mixed states, the next obvious question is, okay, well, how do we evolve this type of states through unitaries or through quantum gates? And this isn't really too difficult to understand if we just remember that, in the case of mixed states, all these really are a collection of possible states, right? So it's really not a superposition of different states, right? It's just a set with some associated probability of occurrence. But if we're running one particular experiment, in that instance, we're only going to be having one of these possibilities passing through our circuit. So, if we apply a unitary U, and in a particular experiment, we have state psi sub 2, then what we get after that unitary is just U applied to psi sub 2. So then, to update this list, all we need to do is just to apply the unitary to each of the individual items, right? So all we get is U applied to psi 1, U applied to psi 2, all the way up to psi sub m, right? Psi sub m. And then the probabilities of occurrence, they don't really change, right? These are predetermined before we have applied that unitary to that particular state. So now the question is, okay, well, this is for an ensemble of states. How do we translate this to the density matrix formalism, right? So we had that the definition of our density matrix is the sum from I1 to M of the outer product of each of the elements in our ensemble, weighted by the probability of occurrence of each state, right? So now we want to know, okay, if I apply that unitary, well, what do we get on the other side, right? So then, rho sub naught is given by, well, we can just basically call this evolved states, phi sub 1, phi sub 2, all the way up to phi sub m. And basically, well, the density matrix for this new ensemble of states is just the sum from I1 through m of pi of phi sub I outer product with itself, right? Now, if we replace this phi sub i's with what they are, which is just U apply on psi 1, well, what we get is p sub I of U acting on psi sub I. And then on this side, what we have is the bra, right? And when we have, a ket and we want to turn it into a bra, what we do is we turn a column vector into a row vector, and we take the complex conjugate of the elements. And that's exactly what we do here. But then for unitaries, what we have to do is take the conjugate transpose, so U dagger. So and that's it. That's the definition of how we apply unitaries to mixed states. So we can also express this as if we have rho evolve through a unitary, what we get is U on rho U dagger, right? U dagger. So that's the same we have up here. So that's basically it. And what we can do next is just look at a simple example of how this works. So let's do it for let's do it just for a pure state, which makes things a little bit easier. But that doesn't mean that this doesn't work for mixed states. So let's say we have the state left, which we've worked with before, which is 1 over root 2, 0 minus I1, right? And let's say we apply an S gate to the state, and what that's gonna give us is the plus state, which is 1 over root 2, 0 plus 1. Okay, so if we want to do this now in the density matrix notation, well, our rho sub L is going to be the outer product of the left state with itself, which, you know, we've derived before. It's 1 over 2 of 1 minus I1, right? And now if we're going to evolve this through the S gate, well, we said we apply S, then rho sub L, and then multiply with S dagger. And this is matrix multiplication. So what do we expect to get? Well, up here, we're expecting to get, you know, we did it with Dirac notation. We get the state plus. So we expect this to match, you know, the outer product of the state plus with itself. So let's see if that's what we get. And just to remind you, this is 1 over 2, 1, 1, 1, 1, right? That's our row out. So let's go down here and say, okay, S rho L S dagger is equal to, well, the matrix for S, the S gate is 1, 0, I, 0. Our rho sub L is 1/2, right? We have it up here. 1/2, 1 minus I, 1, and then multiplied by S dagger, which is 1, 0 minus I, 0, right? So if we multiply, let's move this 1/2 here, and let's multiply this matrix with this matrix. Well, what we get is, you know, 1 times 1 plus 0 times minus I, that's just 0, so we get a 1 in this location, then I, right? And then we move down, so that's 1, and then we have, that's I, right? And then we multiply this again by this other matrix, 1, 0, 0 minus I. And now let's perform that multiplication. That gives us 1/2 of 1 times 1, that's 1, plus I times 0, that's 0. Then 1 times 0, that's 0, and I times minus I, that's 1. And then at the bottom, 1 times 1 is 1, plus I times 0 is 0, so that's just 1. And then 1 times 0 is 0, and I times minus I is 1. So then we can see that these two match, which tells us that the definition of the evolution of a density matrix through a unitary, it's working well. So that's it. So in the next video, I want to use Qiskit, which is a quantum computing software, to show you how you can simulate density matrices and evolve them through unitaries or quantum circuits, and do this a lot easier than just using, you know, pen and paper.